Hi everyone, this is Zhifan Ye from Georgia Tech. I'm a PhD student, supervised by Yingyan Selining at EIC Lab. I'm here to present our work accepted by NeurIPS 2024, titled 3D Gaussian Rendering Can be Sparser, Efficient Rendering via Learned Fragment Pruning. 3D Gaussian splatting has emerged as a promising 3D reconstruction pipeline for its high reconstruction fidelity, as well as fast reconstruction speed, as compared to previous works such as NeurIPS. However, we find that 3D Gaussian splatting still struggles to achieve real-time rendering on the edge devices like AR/VR headsets or smartphones, where real-time rendering is highly desirable for immersive user experience. There are some previous efforts for accelerating 3D Gaussian rendering, for example, compressing Gaussian features through quantization or distillation, but they usually lead to rendering quality degradation. And there are also some works proposed to prune less important 3D Gaussian primitives from the reconstructed 3D Gaussian point cloud. However, they often lead to limited speedup, and the improvement in terms of rendering speed is not proportional to the pruning ratio of 3D Gaussian point cloud. In this work, we want to address the following research question. Can we achieve further speedup without compromising the rendering fidelity of 3D Gaussian splatting in order to enable real-time rendering on edge devices? To address the problem, in this work, we leverage an underexplored opportunity for accelerating 3D Gaussian rendering. So first, through profiling on the edge devices, we identify the rasterization stage as a rendering bottleneck of 3D Gaussian splatting. For example, in this table, we can see that the rasterization stage takes around 90% of rendering time of 3D Gaussian splatting. And the computational complexity of this bottleneck rasterization stage is determined by the number of fragments we have. The number of fragments can be computed as adding up the number of pixels covered by each Gaussian. To reduce the computational complexity of the bottleneck rasterization stage, we propose to reduce the number of fragments we have with fragment pruning. To elaborate, in fragment pruning, we assign each Gaussian primitive with a learnable truncation threshold. In the previous works, all 3D Gaussian primitives are truncated at the default truncation threshold, which is 1 of 225. In contrast, in this work, we allow each 3D Gaussian primitive to learn a higher truncation threshold, which leads to less pixel coverage of each 3D Gaussian primitive, and as a result, reduce the total number of fragments we have. To optimize the truncation threshold of each 3D Gaussian primitive, our learning process is divided into 3 steps. So first, we initialize the threshold of all 3D Gaussian primitive to a default value, and then we approximate the non-differentiable truncation function with a differentiable sigmoid function. And we optimize the truncation threshold of each 3D Gaussian splatting with a photometric loss between the rendered image and the ground truth image. Here are the benchmark results on static scene reconstruction datasets, including MIP-NURF 316, tanks and temples, and deep blending. On all the 3 datasets, our method achieves lossless speedup. So for example, as compared to vanilla 3D Gaussian splatting, our method consistently achieves higher rendering speed on the 3 datasets, while achieve comparable or even better rendering fidelity in terms of PSNR, SSLM, or LPIPS. And our method is also complementary to previous primitive level pruning work. For example, on top of mini splatting, which is a representative work for pruning 3D Gaussian splatting primitives, our method achieves up to 1.71 times speedup, while consistently achieving comparable or even better rendering quality. Furthermore, our method is also applicable to dynamic 3D Gaussian splattings. For example, 4D-GS is a representative work for reconstructing dynamic scenes with dynamic 3D Gaussian splatting. And once apply our method on top of it, we can improve the rendering speed on the panoptic video dataset from 14 to 22, and provide better rendering fidelity at the same time. Thank you for listening. If you have any questions, please feel free to contact me with this email address. And here we acknowledge all the funding sources for their funding support, as well as the NeurIPS 2024 reviewers for their constructive comments and suggestions.